We move on in chapter 18 to our last kind of process in kind of the central heart of mammalian fuel oxidation, which is electron transport and oxidative phosphorylation. So we're going to break this up into a few lectures here, and our first lecture here is going to deal with kind of reminding ourselves where we get our electrons, talking about the purpose and the overview of the electron transport chain, and then importantly thinking about, all right, what are all the players of chemistry that happens in electron transport and oxidative phosphorylation, and how do we get them where we need to be? So we're going to deal with some transport issues, and a lot of the activities that we'll do in class deals with the actual physical creation of a mitochondrion in the classroom, and so we can kind of understand where things are generated, where they need to be, and how we'll need to get them to those places. So just kind of as a neat starting point, if we think about what the human body needs at rest, right? A little bit that more than is required for a 100-watt light bulb. So not that much, and how we kind of come about that energy is using mitochondrial electrochemical events. So transporting, and this is an astronomical number, 3 × 10 to the 21st protons per second. So again, reminding ourselves where those electrons come from. The first activity that we'll actually do in class tomorrow is reminding ourselves about the parts to our basic kind of metabolic equation here, which is mammalian fuel oxidation gives us water, carbon dioxide, and energy. And all of the rest of these arrows we'll remind ourselves with an activity in class where we talk about what it means to be oxidized, the loss of electrons, where those electrons ultimately go to oxygen. But before they go there, and again, this chapter focuses on the delivery of those electrons to the electron transport chain, the generation of a proton gradient that can be used via oxidative phosphorylation to generate ATP. So again, we'll just review that overall equation again. But we've been very carbohydrate focused, so again, we're going to kind of consider that as we move into thinking about some energetics of this process. So we know if we break apart that equation into glucose oxidation, we have a balanced chemical equation for glucose oxidation here, which can be broken into two half reactions, an oxidation and then a reduction half reaction. So this is what we've kind of focused on thus far, is we have fully oxidized glucose into carbon dioxide molecules, and we learned in our citric acid cycle with pyruvate dehydrogenase and then the enzymes of the citric acid cycle how we generate CO2. But importantly, we liberate 24 electrons. And as we've learned, we save those as NADH and FADH2 molecules. So now we're considering the delivery of those electrons as those reduced cofactors to the electron transport chain, where they're ultimately delivered to molecular oxygen and generate water. So again, just like when you think about half reactions in a battery, in order for that to do work, we need to have a conduit for those electrons to pass through. So how do we transport those electrons in our biochemical system here? Again, we put them through complexes of the electron transport chain. This again is just a nice summary to remind ourselves about where we generate these reduced cofactors. So hopefully this is in the forefront of your mind, having just gone through glycolysis, glycogen metabolism, and then the citric acid cycle. So the bulk of what we dealt with in our last chapter in the citric acid cycle, and then again now in this chapter, is chemistry that happens in the mitochondrion. So a good part of the activity that we'll do in class tomorrow has to do with the physical creation of a mitochondrion in the classroom, which allows us to think about these two membranes that we'll have here, an outer mitochondrial membrane, which is very porous, and then a highly invaginated inner mitochondrial membrane, which is highly impervious to most things, but heavily embedded with our proteins of the electron transport chain. So again, I'm not going to go into a lot of detail on this. These will be topics that we'll cover in a good bit of detail in our activity. But again, thinking about a mitochondrion really being two membranes and one that's inside and highly invaginated will allow us to think about how the mitochondrion is able to do this unique chemistry. So kind of a really neat figure here. I love that it kind of peels apart the layers of this lipid bilayer, and all of these little bumps represent proteins. And so what we can clearly see in this yellow inner mitochondrial membrane is there's a lot more bumps, which means there's many more proteins that are there. And we know that all the proteins for the electron transport chain are embedded within that inner mitochondrial membrane. So most of our class activity tomorrow is going to be focused on the creation of that mitochondrial membrane, and then also thinking, who do we need to get where in order to have this chemistry happen. So some of the main players we need to think about are NADH, which again delivers electrons, and then ATP, ADP, and PI. So again, what we're hoping to make in electron transport and oxidative phosphorylation is ATP. But what do we make it from? ADP and PI. So we need to think about getting all of those players to their positions. Again, FADH2 we don't need to think about, because remember we learned in the citric acid cycle the FADH2 that's generated by succinate dehydrogenase is going to be complex 2 of the electron transport chain. So we're going to revisit some of the transporter systems that we've already looked at. So in chapter 16, we learned about the Malate-Aspartate shuttle. Part of your activity is going to be to try to remember where you learned about that and why we learned about it. It's kind of written a little bit here, but it has to do in essence because there's not a transporter for oxaloacetate. So we'll review that in our activity tomorrow. But again, that's going to be a way of getting NADH equivalents where they need to be, whether they're in the cytosol or in the mitochondrion. One of the things I just want to point out here, you'll notice that this says inner mitochondrial membrane, and we really don't show the outer mitochondrial membrane in any of these transport systems. And that's because that outer mitochondrial membrane is so porous. The holes in it, if you will, are so big that for the most part, any small metabolite that's in the cytosol will also be present in that inner membrane space, is what we call it. So that's why we only see one membrane here. A new shuttle system that we'll learn about is called the glycerophosphate shuttle. So I'm not going to go into too many details here in this overview. We'll talk about those tomorrow in class. Transporting ATP. Again, ATP is going to be generated way in the innermost part of the matrix, but it's needed all the way out in the cytosol. And then again, ADP and PI are generated way out in the cytosol when we hydrolyze and use ATP, but they need to be put all the way back in the inside or the matrix of the mitochondrion in order to be effectively made back into ATP. So we have this transporter that basically can transport both of these kind of in a similar mechanistic way as we saw with our glucose transporters. So we'll talk a little bit more about that one tomorrow. And lastly, the inorganic phosphate and then proton symport. So remember, symport moves things in the same way. So we'll talk about the direction that this will work and also how this is going to facilitate and piggyback the input or the influx of inorganic phosphate with protons. And so we'll talk about that shuttle as well, or that transporter tomorrow. All right, big picture here, and we'll have some activities that deal with this. We have, and look in here, this is going to be an important thing, NADH delivers its electrons all the way on the innermost part of the mitochondrion and what we call the matrix. So again, this is where electrons are input. They go through complex 1, complex 3, and complex 4. And we're not going to get to the details of this until the next couple of classes, but we also see that there's a couple of mobile carriers here, either one that's hydrophobic and embedded in the lipid bilayer, or one that's hydrophilic and exists kind of in this inner membrane space that allow us to move these electrons between these complexes. And we'll learn in our next few classes how each of these complexes are able to translocate protons and thus generate that proton gradient. Because remember, the purpose of that proton gradient is we're going to dissipate that proton gradient, and we're going to kind of operate, it looks kind of like a merry-go-round here, this complex machinery that allows us to synthesize ATP. So that's kind of the big picture overview of electron transport and oxidative phosphorylation. So we'll spend a little bit of time, don't be scared of the math, but we're going to use the Nernst equation and kind of think about, hey, this is a lot of energy that we have here from the energy that's contained in NADH, way more than is necessary to make one ATP Remember that number, 30.5 kilojoules per mole. So this is a lot more than is necessary to make ATP. And truthfully, it's a lot more than even to make 3 ATP, which is what we know NADH is worth. So it's not a fully efficient process, but it's an efficient enough process. So I have these two figures kind of lined up in kind of a weird way to remind us that there is a change in the standard reduction potential as we go through these complexes. So you can think of electrons starting out as a high energy level chemically, and as they go through these complexes, they become energetically less value from a redox standpoint. I'm not going to go through any more details on this slide. We'll talk about it as it's relevant with a couple of questions tomorrow. But big picture, all I want you to remember is that we kind of step down in terms of our chemical value, if we will, as we step to and change the redox potential. And that's all important and relevant because remember, when we're in an enzyme active site, the standard reduction potential can change depending on the environment. Maybe you remember from Gen Chem, you had like a table of standard reduction values that had different metals and their kind of reduction potentials. You know, copper 2 plus 2 electrons made copper solid, and that was worth a certain number of volts as a half reaction. Well, what we see in biochemistry is when you put these metals within the context of an enzyme active site, we can tweak that redox potential because we've tweaked their environment. So that microenvironment is really important, very similar to what we saw like for pKa values. All right, so again, just summarizing here, and I know this figure looks a little weird. This is intentionally upside down. I hate that your book kind of does this. When it shows this initial picture right here, it has it truly in the opposite direction of where we see it in the electron transport chain. So I wanted to make sure to put all of these pieces together so we can remember all of the processes that happen on the matrix side. So we can see ATP is generated on the matrix side, NADH enters on the matrix side, protons are pumped out of the matrix into the inner membrane space, and again back through complex 5 to generate ATP. So again, that's all we'll get to in terms of the details of electron transport. We'll begin to understand the details of these complexes in the next couple of lectures. And that's it for an introduction to the electron transport chain and oxidative phosphorylation.